Okay, I'm going to start here by talking about electron spin. And it is important because it's one of the things that guides how we fill the orbitals on the quantum mechanical atom with electrons. In quantum mechanics, it turns out that an orbital can only hold at most 2 electrons. So it can either have 0 electrons, 1 electron in it, or 2 electrons in any one orbital. And then there's another restriction called the Pauli Exclusion Principle, which says that the electrons, if they're going to be in the same orbital, they have to have different spin quantum numbers. So you need to sort of have an idea of what spin means in order to know what a spin quantum number is. So that's what I want to show you right here with a little picture of an electron. Let's say this is an electron, and we're just going to assume that it's a sphere that has a charge. So you know the electron has a negative charge to it. Well, if you think of it as a sphere with that negative charge distributed over the surface of the sphere, and we also consider the behavior that when electrons travel through space, or let's say through a wire, that they produce a magnetic field. It's known experimentally that particles, charged particles like electrons and protons, they have a magnetic field around them. And one of the simple ways to think about it and to sort of model that is to imagine that the particle itself with its charge is spinning. Because if it's spinning, that means the charge is in motion. So let's say the electron here is spinning this direction. Okay, so if it's spinning that direction like a top, it's just spinning on like it's on a table and spinning, then the electron charge that's on the surface is moving around as well, the same direction that it's spinning. And so if we think about that as a moving charge, then it's going to produce a magnetic field. So the particle itself is going to exhibit a magnetic field. And the magnetic field, if you think about it going like this, for this particular one, the magnetic field is going to be pointing down. And what that means is that down would be the north pole of the magnet, but then the field lines would also go around and come in the other way, like that. So they would go in at this point and down at that point. This would represent a spin down type of situation. And when we solve the Schrodinger equation for the wave function of an electron, its spin is part of the solution for that wave function. So it turns out that the value that comes out of the Schrodinger equation for spin is either plus or minus a half, depending on whether it's pointing up or down. So pointing down, for that situation, the spin quantum number, which is designated m sub s, would be equal to minus a half. If we put the electron rotating in the opposite direction, so I'm just going to keep that same picture up there, but change the direction of rotation, then it turns out that the spin, or the magnetic field would be the opposite direction. So if it starts here and it's spinning this way instead, so that the charge is moving this way on the surface, then with the rule that we'd use for the direction of magnetic field, it would be coming out of the top. Okay, so you'd have an arrow coming out the top, but then would also have field lines going around it like this, and this would be the north pole of the magnetic field, and in this situation, this would be a spin up. The spin quantum number, m sub s, would then be equal to plus a half. Okay, so that would correspond to an up spin. And if just to forget about the particular number of 1/2 or plus minus or minus 1/2, if we just think of the two spins as being in opposite direction, one being up and one being down, then we can say that quantum mechanics requires that any two electrons that are in the same orbital have to have opposite spins or different spin quantum numbers. Another way to say that is opposite spin. So let's see how that affects the way that we put the electrons on the atom. And when we do that, when we show where the electrons are arranged on an atom, that's called an electron configuration.